A fan advertised at 23,300 cubic meters per hour may deliver only 4,580 at 300 pascals. Those are 2 points from the same Longwell AC800 axial fan specification. Nothing is wrong with the fan. The first number is free airflow at zero static pressure, the second is a real operating condition. That gap is why choosing axial or centrifugal by maximum airflow is risky. Here is a practical 6-question method that gets you to the right shortlist, without pretending one fan type is always better. First, understand the geometry. An axial fan takes air in and sends it out roughly parallel to the shaft. It gives you a straight-through flow path and a large swept area in a shallow package. A centrifugal fan takes air into the eye of the wheel, turns it, and discharges it radially. A scroll or equipment plenum then collects that flow. The turn is not a magic pressure generator, but centrifugal geometry is commonly developed for higher resistance systems. Second, define one duty point, required airflow and required pressure at the same condition. State whether the pressure is static or total, and include air density if temperature or altitude is unusual. The fan curve falls as flow increases. The system curve rises, often approximately with flow squared. Their intersection is the operating point. A maximum flow number, a maximum pressure number, and a motor wattage are not an operating point. Now ask the 6 questions. 1. What is the pressure at design airflow? A short, open path with modest resistance often puts an axial fan on the shortlist. Filters, coils, silencers, dampers and long ducts add resistance and often move a centrifugal fan onto the shortlist. Often matters, the actual curves can overlap. 2. Must the airflow remain straight through? Condensers, dry coolers, cooling towers, and wall ventilation frequently favor axial geometry. If a side discharge, compact plenum, or controlled outlet direction helps the equipment layout, centrifugal geometry may fit better. 3. What space is genuinely limited? Axial fans are usually shallow in the flow direction, but need face area. A plug fan may be deeper yet integrate efficiently into an air handler. Compare the complete installation, including inlet clearance, guards, transitions and service access. 4. What is in the air? Temperature, moisture, grease, dust and corrosive gas affect blade material, coating, motor protection and cleaning access. They can change the correct wheel design within the centrifugal family, or rule out an otherwise attractive axial package. 5. Where are efficiency and sound measured? Compare both candidates at the required duty point and the same test boundary. Check absorbed electrical power, total efficiency, and the sound spectrum, not one headline decibel value. A quiet fan in free air can become noisy behind a poor grill or distorted inlet. 6. How will the system operate? Check speed control, part load hours, redundancy, fault reporting, and maintenance. These are motor and system decisions, not automatic advantages of either airflow geometry. Consider 2 common cases. An outdoor condenser needs high airflow across a broad coil, a straight path and a shallow cabinet. Axial is a sensible first candidate, but the coil, grill and wind conditions still set the operating point. An air handling unit must pull through a filter and coil, then feed ductwork. A backward curved centrifugal or plug fan is a sensible first candidate, but it still has to prove airflow, pressure, efficiency, sound and stability on its tested curve. So the answer is not axial for airflow, centrifugal for pressure. The useful answer is, calculate the system duty, use geometry to form a shortlist, then verify the curve in the real installation. If you already have airflow, pressure and an installation drawing, Longwell can help review the shortlist.